Up till now, we have seen queuing systems from the producer perspective. Now we are going to see queuing system from the consumer perspective, and for this we are going to discuss queue based load leveling pattern. Now this is very easy pattern. The gist of it is like when you have a system or have multiple systems which want to get a particular work done by a single system, then what is going to happen is they are going to directly call this system. And if these systems have different load patterns, then there can be chances at some point in time it is going to create bursts of traffic to this system. So what is going to happen is it is going to affect availability of this red system. So what you can do is, instead of directly sending request to your target system, what target system can do is it can create a queue in front of it so that all the requests are basically being queued in the queuing system. All the producers or all the callers are basically sending their request in the queue, and this queue is acting as a buffering system or as a load leveling system so that this consumer or basically the target is reading these requests from the queue at its own pace. So even if during some circumstances there is high load on our queuing system, on our target system, it is going to be absorbed by the queuing system. What is going to happen is during high load, the queue length in these system or in the queuing system is going to increase, but it is not going to impact our target system, and it is going to improve the stability of our target system. It can also help us in another way. For example, if our target system is down for some reason, it has crashed altogether, what can happen is if there was a direct coupling between callers and the target system, then callers won't be able to access the target system's functionality, and they will have to handle or make a retry logic at their end. But rather than this, if they are using, if target is using a queue based load leveling pattern, so callers are just sending their request in the queuing system, and these requests are getting queued. So even if our target system is down, these requests will continue to get queued as per the allowed queue length, and when the target system comes back online, it is going to consume these messages from the queue and respond to the requests that have been provided to it. Now this provides us another functionality or another advantage. That advantage is if you want to give different level of priorities to different callers. For example, if it is a high priority caller and this is a low priority caller and this is a medium priority caller, so what you can do is you can create, a target can create different queues for different priority consumers or different priority callers, and hence we can use priority queuing mechanism in which the messages for the high priority caller is going to be queued in high priority queue. This is medium priority queue, this is high priority queue, and the SLA of consuming messages from high priority queue is going to be higher than SLA for consuming from low priority queue. So it is going to handle, queuing mechanism can handle the priority of the messages from the service, and it is also handling scaling of our systems. So we can basically scale as per the queue length in our system, scale our target system as per the queue lengths which are present in our system. Another advantage this queue based load leveling pattern provides is if we had direct integration between these services, then target system had to be scaled according to the peak load that it can expect from its callers. But since we are not handling the peak load, what we can do is we can keep our system scaled according to the average load that target can experience, and peak loads can be handled by our queuing system. So it is going to control our costs. Now we also have to consider the case where callers are expecting a reply from the target. So if it is a one-way communication, then it is okay that callers are just sending the request and done with the request. But if they expect a reply from the target, then it becomes complicated. Then you may have to use asynchronous messaging systems or a messaging pattern in which you can either create a reply queue where in which the target can provide a response, or what you can do is you can create a facade before your final layer. So for example, what is going to happen is all the callers, caller 1, caller 2, caller 3, are going to call a service which is just a facade over a queue. All the messages are going in a queue, and here this is the target system. So even the peak loads are being handled by the main system. All the requests are coming to this facade or adapter or whatever you want to say, wrapper, and then target is consuming from the queuing system, and when the target has processed the response, it is basically sending the response back in a response queue which this facade layer is reading, and then it is correlating the request ID. When messages are being published in the messaging system, it is sending a request ID, and for example, this is request 1, so it is sending R1, and when the response is coming back, so it is it is providing that it is request for response for R1. Then this facade layer is basically stitching or correlating the request and response and sending the response back to the actual caller. So here callers C1, C2, and C3 are not aware that there is any queuing mechanism happening in the target ecosystem, but all the major load handling or all the major work that is being done by the target has been load leveled using a queue, and real-time request responses are being handled by a facade layer over the request and response queues. So this is how you can handle request replies over a queue load leveled pattern. Now, even if we have load leveled or load balanced the target load using a queue, but we cannot scale this target infinitely, because if we are going to scale this target, let's say it is T1, it is T2, and it is T3. So we have basically auto scaled or scaled our target so that it can handle more load. But what will happen is, suppose if this target, if this target was dependent on a database, then it can become the next level in your ecosystem can become a bottleneck, because the number of requests that will be sent to the database can choke the database. So here also you will need to have queuing system so that database is also handling load by a queuing system. So what will happen is your ecosystem is going to look like this. All the requests are coming here. Then you have target ecosystem where you have T1, T2, and T3. Then it is sending to the queue for the database or your next service. So let's suppose this is another service, S1 to S3, and this can go on forever, or this pattern can go on forever. But the main point is you cannot scale any chain in your ecosystem infinitely without considering the repercussions on its downstream services, because if you scale this service, then it can overwhelm its next service, and if you scale this service infinitely without considering its downstream service, then that downstream service can be harmed. So you have, whenever you are auto scaling these types of systems, you have to consider what is going to be its impact on the other services, on other downstream services. Now, this pattern is actively used by a database called Elasticsearch. What happens in Elasticsearch is any request that you are sending to Elasticsearch instance, let's say this is your instance, and any request, whether it is read request or write request that you are sending, it is queued in the separate queues. For example, this is the search queue and this is the bulk queue. The read requests in Elasticsearch are called search requests and the write requests are called bulk requests. So all these requests are first sent in their respective queues, and as per the Elasticsearch bandwidth, they are consumed by the Elasticsearch. So for example, if let's suppose this is your service and this is your ES, this is all part of ES. This is part of ES. These queues are basically internal to the Elasticsearch process or Elasticsearch program. They are present in each of the instances. So if you have two instances, each of them is going to have a different search queue and bulk queue. And these requests are being queued as per the number of requests that are coming. So if for example your Elasticsearch gets lot of requests, read requests, so these read requests are going to get queued, and if this queue length exceeds a particular amount or particular decided configuration, for example, if this queue length exceeds 1000, then 1001 request is going to get dropped. You are going to get 429 from the Elasticsearch. In all the previous systems, we have seen that these queues were external to the process, target process. But in this case, these queues are being maintained internally to Elasticsearch. So what can happen is, if the requests are not evenly load balanced, so your read request on a particular instance can get 429, whereas read request on another instance, which is not getting a lot of requests, can serve the traffic. So this is real time, or this is a real life usage of queue level load balancing pattern, which is used in Elasticsearch. I hope you enjoyed the video. Please let me know your views in comments. Thank you and have a nice day.